Hey, I'm Amy Wang, and this is my Lab 2 report about the motion of a falling object and how gravity and drag force affected that motion. The objective of this lab was to quantify the motion of the object, which in this case was a sugar packet, as it is affected by gravity and then as it is affected by both gravity and drag force. To understand these forces, we are going to use Newton's second law of motion. For this lab, I filmed myself dropping a sugar packet and analyzed the video in Tracker. The motion was then modeled using this code in VIDLE. The computational model and the experimental model were then compared to understand that there was a net force acting on the sugar packet and that the object had reached terminal velocity. So now let's look at Newton's second law in detail. The law states that force equals mass times acceleration, which then derived gives us final velocity equals initial velocity plus F net over mass times delta t. In this case, we know that F net does not equal 0 because velocity is not constant. There has to be other forces affecting our object, which in this lab are the forces of weight or gravity and the drag force. Now let's watch the video closely. The sugar packet is my system and everything else is the surrounding. The points are taken and drawn on this graph over here. The graph seems to be curved here at the beginning, which means there is acceleration. It becomes more linear down here, meaning that the sugar packet begins to move at a constant velocity near the end, reaching terminal velocity. First, we had to calibrate the video by using these blue calibration sticks to state the measurement of both the sugar packet and myself to make the data more accurate. I then placed an axis here with y positive going up and x positive going right. The axis is tilted at a 1.4 degree angle to make it easier for me to track and record the data. In this lab, we are only looking at the y-axis to judge the position of the object as it falls toward the negative y direction. I took the information of initial position and final time and plugged it into the given code in VIDLE. I also included the mass of the sugar packet, a small delta t, and the gravity constant of 9.8. I also plugged in the velocity and the position equations, which both can be derived from Newton's second law of motion. I will then run this module, but keep in mind that the weight force is the only thing I have included for the net force. The blue line is the model that we get from running the module. It is actually pretty different from our observed data, which is the red points. The model overpredicts what happens. The reason the two graphs do not match is because we did not include the other force acting on the sugar packet, and that's the drag force. I will include drag force in the code by using the turbulent velocity equation. The b in the equation is the proportionality constant, which I calculated to be 0.00044 by matching the final model prediction to the final observed position. The turbulent velocity equation can also be written like this in the module. Now let's look at the code. We have included the proportionality constant here and the equation that we wrote here. So now F net equals both weight and drag force. Let's run the code. We will now take the data points received from running this code and put them into Excel to compare to our other data. The new model, the green model, including weight and drag force, is more representative of the observed data. The difference between the two could be due to human error or assumptions that were made. In conclusion, it can be said that the object will experience terminal velocity because of its large drag force. The sugar packet is an object that drops slowly with more surface area and less density. To prove the motion of my object had terminal velocity, or very close to having it, I checked the slope and change of slope in Excel. I calculated slope by doing position over time for each point. I calculated change in slope by doing final slope minus initial slope. I then averaged these last few change in slopes to be negative 0.007. I chose these points because I thought that was when my object was reaching terminal velocity. If I had dropped the sugar packet from a higher point, I probably would have gotten a number closer to 0, meaning terminal velocity was even closer to being reached. Let's answer the first question of what does it mean. We can do this by looking at the velocity versus time graphs of both models. The first model includes no drag force, so there is nothing canceling out the weight force, which means terminal velocity cannot be reached. The second model predicts terminal velocity better because velocity becomes constant after a certain time, which means the object reaches terminal velocity. Now let's look at the second question of what if. We can model an object being thrown by changing the initial velocity in our code. We can do this by changing the y value to something like negative 15 meters per second. After being ran, the resulting velocity versus time graph should look something like this. The velocity is actually decelerating first because the drag force exceeds gravity, but the velocity still becomes constant after a certain time, up here. The terminal velocity reached here should be, at the same time, an equivalent to the originally observed one, because it depends on things like mass, density, and surface area, which do not change. And that's the end of Lab 2. Thanks for watching.